Okay, folks, I hope you had a good weekend. It's an interesting first week. Um, we'll try to figure out how to work out these video lectures for you. Like I said, if there's any comments, you guys can help me out and try to figure out how to go about making these lectures run a little bit more smoothly. Hopefully, the amount of time that I give you to do the problems are enough. It seems like more of you towards the end of the week were able to get the work in on time. So, you know what? Keep up the good work. I think you folks are doing a really good job considering everything we have to deal with here. So, and now this week we have a new schedule. We're going to be shifting to the Fridays Friday schedule. I think it's schedule number 4 every day now, and so that shortens our period even more. I'm gonna tweak the video lessons a little bit more. Obviously, I can't make them as long as I did before. What I'm gonna try to do is cut down on the amount of work that you have to do in the video lesson, so there'll be less practice, but hopefully you'll be able to get some of the work done on your own. On Friday, I apologize during the Zoom tutorial session on Zoom after school. I had some issues with the connection, so that I lost the connection there. So a few of you looked like we're trying to get on. I think I have all of the issues worked out. So this afternoon, if you have any questions, stop by the Zoom tutorial 3:15, 4:15. I'm sorry. Uh, I'm getting used to the new schedule too. I think it should be about 1 to 3. But, I'll keep the tutorial session the same, 3:15 to 4:15. If you can get on at that time, I'll be on, and you can ask your questions then. So again, tutorial will be at the same. The tutorials will be at the same time still. We get out of school a little bit earlier, and so you'll have a little bit of break. You'll have some break before we start the tutorial at 3:15 to 4:15. So I hope I see more of you after school, but please make sure you come by and get your help if you need it. Okay. All right. So let's continue on here. Let's pick up where we left off with on Friday. I'm going to start the clock here to make sure then that I stay within the time frame that will be workable for you guys. Okay. So I'll try to stop on time. Um, so we left off on Friday with the discussion of lattice energies. We saw then that there was this lattice energy. There was this exothermic process, this drop in energy that allows then ionic solids to form. The lattice energy is essentially the energy of different ionic, the different ions, the cation, the anion that were initially in the gaseous state. Then they get together in the solid state. They form this crystal lattice, and so that as a result, then they get closer together. And because they get closer together, we saw then with Coulomb's law, when we solve for the energies, the closer these charges are to one another, the greater that lattice energy is, because the stronger the force of attraction is between the two ions. And so there are a few problems I want us to try to do here. These are number 55A through C from your book. And so this will be this was part of your homework from set A. So I just want to quickly go over this with you. And remember then, when we talk about this lattice energy, and so let me go ahead and switch the color of the pen here. We were using a modified version of Coulomb's law. We saw then that this lattice energy is equal to the constant, this constant here, which is similar to the Coulomb's constant here, times the product of the ratios over the product of the charges, sorry, all over the distance between those two charges. Okay, so keep this in mind as we go through number 55A. So please make sure, go ahead and get your books if you have it. I'll pause a moment here for you to get your books. Okay, and then I'm going to work through 55. So I'd like to work through number 55A through C with you. And this is all at I forget what page it's on. Sorry, I don't have the book in. But 55A through C at the end of chapter 8. Okay, let's go ahead and work through those. All right, let's take a look at 55A first. Okay, and let's take a look at it. They ask us then between these two compounds here, sodium chloride, and potassium chloride, which one of these compounds has the greater lattice energy? Okay, which one of these, meaning then, which one of these compounds here is the attraction between the cation and the anion stronger? Okay, so let's take a look at this here. The difference here between these two compounds is in the cations, the sodium ions here and the potassium ion here. Now, with all these problems here, make sure you understand this is what we're going to use. We're going to use the Coulomb's law here in order to determine the lattice energies. And so that lattice energy is going to be dependent on the charge. This is constant for both of these, and that won't be different. It's going to be dependent on the charge and the distance between them. Now, obviously, the charges for these two will be the same because then the sodium ion and the potassium ion are both positive ones, and the chlorides are both positive ones. So that can't be the reason why one of these has the greater lattice energy. Again, what we want to make sure we keep in mind then is the question's asking us, of these two compounds, which one has the greater attractive force between the ions? Okay? All right. And so if it's not the charge, it has to be then this here, the distance between this ion and this ion and this ion and this ion. So R has to be different. So how is R going to be different then? Well, it depends on how close these ions get to one another, and the distance these ions will can get to one another is going to be dependent then on their size. Okay? And so with that said, then we take a look at this. Of these two, the potassium ion is larger than the sodium ion. The potassium ion is larger than the sodium ion. They're both in the same group, both 1A elements. They're both alkali metals, and so potassium's down beneath sodium. It's a larger ion, meaning then chloride and potassium cannot get as close as sodium and chlorine can get to one another. So therefore, the lattice energy for sodium chloride is going to be greater than the lattice energy for potassium chloride. And the reason for that, again, is that the size, and we'll talk about this, the size here, and I'm sorry, let me go ahead and do this. The ion size, and we learned about this back on Thursday, about ion size. We talked about the sizes of the atoms within a group and the atoms within a period. And then we talked about isoelectronic series. And so therefore, the reason why sodium chloride is greater, we can essentially say then that the R, the distance between sodium and chlorine, is going to be smaller than the R for K, potassium, and chlorine. Okay, so if R is smaller here, the lattice energy is going to be greater. So all that goes to answering then why the lattice energy for sodium chloride is greater than the lattice energy for potassium chloride. Okay. All right, let's go ahead. So ion size and the distance between them. Let's go ahead and take a look at 55B. 55B is asking us now between lithium fluoride and lithium chloride, which one of these compounds has greater lattice energies? And if you take a look at this again, you'll see then that the cations this time are the same and the anions are different. So we're going to go about answering this question here in much the same way we answered number 55A. So let's go ahead and compare. We have the fluoride ions and the chloride ion. Of these two, which one's smaller? Well, we know then that with these two then, the fluoride ion is smaller. Okay, so again, we were dealing with the ion size here. Okay, so the size of the ions here, the fluoride ion is smaller than the chloride ion, which means then, yeah, again, we go back here, the charges are not different. It has to be R. The distance that the lithium fluoride compound, the lithium and fluoride ions can get to one another versus the lithium and chloride ions, this will be smaller. Okay? R then meaning then that the lithium ion can get closer to the fluoride ions, so the distance between them is smaller. If the distance between them is smaller, the lattice energy for lithium fluoride is going to be greater than the lattice energy for lithium chloride, and that's going to be our answer right there. Okay. All right. Let's go ahead and let's take a look at the last one. I just want to do the first three with you. I'm going to leave the remaining three for you to do, so please make sure you take a look at that and combine. See me if you have any questions. Good. The last one asks us about the magnesium hydroxide versus magnesium oxide. Oh, sorry, magnesium oxide. Okay. Okay. So let's go ahead and let's take a look at the difference now. The difference here then, the cation or the cations are the same for both compounds. The anions are different now. So let's go ahead and take a look at this. The anion here is hydroxide, and the anion here is the oxide anion. Okay. Now, if we take a look at this, then the difference now here becomes a little bit more apparent because here now we have a difference in charge. So the charge for a hydroxide ion is less than the charge for the oxide ion. This is 2 minus versus 1 minus here. And yes, we do have 2 here, but the charge in each one of those ions is less. So therefore, we're going to look at the ionic charge in this one rather than the ionic size. Okay. And so with ionic charge here, hydroxide is smaller. It has a smaller charge than oxide. Okay. And because of that, the charge on hydroxide is smaller than the charge on oxide. Okay. If that is true, then magnesium oxide will have the greater lattice energy, the greater attraction between the ions. Okay. All right, so that means then the bond here, the bond between magnesium and oxide here is greater than the bond between magnesium and oxygen, but between magnesium, each of the oxygens. Okay. All right, so that kind of was a qualitative way that we can go about assessing lattice energies. Okay. And so if we can do that, we're using ionic size, you're in a pretty good shape because you have to be able to assess that. Okay. All right, so with that said, then let's go ahead and let's calculate. Let's use this lattice energy. Okay? So we talked about what the lattice energy is and what we can do to calculate for it on Friday as well. And so what I'd like to do then is let's go ahead and use the lattice energies here to calculate for what we call then the delta H, the enthalpy, the standard enthalpy of formation for this particular compound. And we were able to work through a problem like this. I talked to you about this. We talked about this. We saw an example problem. And so I want to work this out with you. Okay, I want to work this out with you. This is number 58 in your textbook. Since you have it open, go ahead and take a look at number 58 in your textbook. This should help you with your homework that you will be doing tonight. Okay, so let's go ahead and let's take a look at it. Okay. All right, so what we want to do then is, let's first of all, we want to set up here the reaction, the bond that we want to see form, the chemical reaction essentially is going to be between magnesium, solid magnesium, the fluorine, okay, as a gas, and then we want to form then magnesium fluoride solid. Okay, so this is the process. This is the reaction that we want to examine as we go through this. We want to find the delta H standard. So this is the energy needed to form this compound here. Okay, so what is that going to be? Okay, so what I would just do is write this out. So first of all, what we have to do, remember, is we want to make sure then that we identify, we have to make the solid here a gas first. So therefore, we have to convert the magnesium solid into its gaseous state before we can ionize it. Okay, and so therefore, this is known as the enthalpy or the energy of sublimation. Okay, so I'm going to write that as the enthalpy, the heat, the enthalpy of sublimation. And that was given to us on the previous slide then as I think, let me take a look at right here, 150. So this is a positive 150 kilojoules per mole. Okay, so keep that in mind. All right, so that's the first step in this reaction. So we got to sublimate. We have to make the gaseous form of the metal first. Okay, and then what we can do is we can take that metal in the gaseous state and we can ionize it. Okay, which means then we form the ion. But remember, ionization takes place in a step-like manner, and so therefore, let's keep this in mind. We start out with 2 valence electrons here. We're going to lose 1 first. First ionization energy they give us, and so with that first ionization energy, we form magnesium with a 1+. This is going to be the ionization energy, okay, number 1, and that they give us then as a positive 735 kilojoules per mole. So first ionization energy is always going to be less. Okay, so we have that. And then what we have to do remember this ion is a magnesium 2+ ion. This ion has to go through the second. Okay, so we have a plus, second ionization energy, where it loses a second ion, second electron. Okay. Then now it becomes 2+. Okay. And this is going to be the ionization energy 2. And this one was given to us as the second ionization energy as a positive value for 1,445 kilojoules per mole. Right. So now we have one of the ions that make up this particular compound. So there it is. There's the magnesium ion. Okay. Now we got to deal with the non-metal part of it. Okay. So fluorine then. Fluorine here, you have to make sure you understand this bond has to break first. Remember, that bond has to break to form the fluoride anion. So we have to use the bond energy to get then 2 fluoride ions in the gaseous state. Okay. So this is our bond energy for fluorine. So this is going to be the delta H, and it's going to be the bond energy for fluorine. And they give us this then as positive 154 kilojoules per mole. And understand what we're saying, what we're doing here, what this step is telling us here is that the fluorine single bond here has to break up to form 2 of the fluorine atoms, neutral atoms here. Okay, so that's the what the bond energy refers to here. Once we have the fluorine atoms separated, okay, each of the fluorine atoms now have to be ionized, which means then we're going to deal with the electron affinity to form the fluoride ion. Okay. Now you have to keep this in mind. There's 2 of them here, so we have to ionize 2 of these. Okay. So don't forget that we got 2 here, so we got to ionize 2 of them, and so therefore the electron affinity for this then, we know the electron affinity for one atom of fluorine is negative 328 kilojoules per mole. But again, like I said, we had to ionize 2 of them, so we got to double. We have to double that particular ionization, that electron affinity. So don't forget this, or else your numbers will be off. Okay. All right. So now there we have the fluoride ions, and here we have the magnesium ion. Remember the last step then, and both of these are in the gaseous state. The last step then is we got to take the magnesium ion in the gaseous state, and the 2 fluoride ions in the gaseous state, and bring them together to form then 1 magnesium fluoride compound. And in the solids, that means they all come together. And this then was our lattice energy. So that's the lattice energy here. We were given that as negative 2,913 kilojoules per mole. Okay. All right. So using Hess's law then, folks, just remember, if you add all that up, if you add all these up, for example, this will cancel out, that will cancel out, this cancels out, that cancels out, okay? I'm sorry, this is magnesium. And then this will cancel out here with here. So all of them will cancel out, so that we will end up with the equation we started out with at the top, which is magnesium plus fluorine gas gives us magnesium fluoride solid. If that doesn't, if these don't cancel out here to give you this final equation here, you did something wrong. Okay. All right. So with that said, we're adding everything up over here on the left-hand side. We're going to add up all of these energies here as well. So you got to add up all of these equations. You're going to add up all of these energies here, and that is what will give us the delta H, the standard enthalpy of formation, the formation. And that gives us then a value of negative 1,085 kilojoules per mole. And that, folks, is our answer. Okay. All right. So hopefully, these problems end up being very simple, folks. They're not going to be very difficult. And so, work this out there. You'll get a chance to practice a few of these problems today after school for homework. So please make sure you get that done. Okay. But the question then is, like I told you, the lattice energies we usually don't we can't measure it directly. I already mentioned that to you on Friday when we talked about lattice energies. So we have to take these energies here that can be measured to find this lattice energy. So how do we go about doing that? What's the process by which we can do it? Well, we saw that we can use the Coulomb's law if we needed to, but there's a way that if we could calculate, if we can measure these energies here, we can calculate it out as well. And that's using what's called the Born-Haber cycle. Okay? Now, the Born-Haber cycle then is just basically a process, a calculation that we can use in order to determine then the lattice energies. Now, we can also use the Born-Haber cycles to find any of these energies, whether it's electron affinity, ionization energy. We can use that process here to find any of those energies. But what I'm going to do is I'm going to show you how we can use the Born-Haber cycle to find the lattice energies. Okay? But just keep this in mind. We're going to make use of Hess's law here. And as a result of that, we can go ahead and if we don't know, if we are missing one of those energies, we can find the energies for the other one. Just keep this in mind then. What we're going to do is we're going to take into account all of these energies here. So again, the sublimation of the metal, which is going to be an endothermic process. We saw that already. Ionization of the metal atoms, that's also endothermic. Dissociation energy for the non-metal atom, that's going to be endothermic as well. The formation of the non-metal ions, that's going to be exothermic. That's your electron affinity. And then the lattice energy is right here, the formation of the ionic solid. We're going to make use of all these energies. We're going to try to, and then we're going to use this here. And also we're going to make use of the enthalpy, the standard enthalpy of formation, that delta H of formation, to find then the lattice energies here. Okay, so with that said then, let's take a look at an example of a problem where we're going to form, let's take a look at magnesium oxide and how it forms. Okay, so let's go ahead and let's take a look at how we would go about doing this. Okay, so we're going to use the Born-Haber cycle then to find the lattice energy. Okay, so we know this. Let's go ahead and with the problem we just did, we saw then that the delta H of formation is going to be equal to the sum of all of the energies that are associated in this formation. So we got the delta H of sublimation, okay, which was an endothermic process. The delta H of ionization energy, which is also a positive value. Okay, we can add that together. We can add to that then the dissociation energy, the bond energy that we talked about. That was also a positive value. Okay. And to that we added the electron affinity. And we saw that that was a negative value. That was an exothermic process. And then finally, then we had then the lattice energy, delta H for the lattice energy. And we saw then that was a very negative value. Okay. All right. So with that said, then you can imagine that if we're going to try to find this lattice energy here, if we're going to find this lattice energy here, we will end up with a negative value if we do this all correctly. So let's go ahead and solve, if we're going to try to find the lattice energy. You can imagine then that we're going to subtract from the enthalpy of formation the sum of all of these here, which is going to be the delta H of sublimation plus delta H of ionization energy plus delta H bond energy, dissociation energy, plus the delta H of the electron affinity. Okay? And if we add all those together correctly, we plug them in correctly, we should end up with a negative value here for lattice energy. If we don't, then we did something wrong here. So basically then we're going to sum all the what we know here and subtract it from delta H. Okay, so this is essentially the Born-Haber cycle. We can use this process here to solve for lattice energies, but we can easily use it to solve for ionization energy, bond energy, electron affinity, any of these here. It's just going to be simple algebra. So if you compare bond energies here, like we said, and we'll just take a look at magnesium oxide here, you can take a look at this then, and you can see how large the lattice energy is here for magnesium oxide. Now, I'm running low on time here, but I want you to think about this here. Okay, we see then that it takes a lot of energy to produce this oxide ion here and the magnesium ion. We had to go through 2 ionizations for magnesium and 2 ionization energy electron affinities for oxygen. Okay? And so the question then is, why would this even form? Well, it forms because the lattice energy is going to be very large. The reason why magnesium oxide is formed between magnesium Mg2 plus and O2 minus rather than Mg plus and O minus is because this lattice energy between them is going to be very large. So you got 2 very the charges here are going to be greater than the charges for magnesium ion and just the magnesium plus 1 plus and the oxide 1 minus. Okay, so the lattice energy obviously then is going to be greater, else this doesn't form. Okay, and so we see here then, as a result of this, okay, the overall energy change here is going to be minus 602 and 570 here. Magnesium oxide is going to be a stronger bond than the sodium fluoride here. Okay. All right. Let's go ahead then, and I'm going to ask you to do one problem here. Okay, so let's take a look at number 61 in your from your homework. And so this is in your book. Let's take a look at number 61. Let's take about a minute, a couple minutes. What I'd like you to do is set up the problem. We're going to use the Born-Haber cycle here. We're going to use this time to calculate for the energy of sublimation. So take about a couple minutes to set up the problem. I think it ends up being pretty straightforward, and then I'll work it out with you, okay? Okay, let's go ahead and let's take a look at this problem here. Let's first of all identify what we have. Okay, what we have here then is the reaction. Let's go ahead and write this out. We have the reaction between lithium in the solid state and iodine in the gaseous state to form for us the lithium iodide, the compound. Okay, and we're told then in this problem, we're already told that the standard enthalpy of formation is. We're given that, and so make sure you're able to recognize that. So that's going to be 292 kilojoules per mole. Okay, okay. So let's go ahead and list what they give us. Okay, we are given the lattice energy. In this problem, we are given the lattice energy. We're told then that's negative 753 kilojoules per mole. Okay, we are also given the ionization energy for lithium, and that we're told that is a positive 520 kilojoules per mole. Sorry about that. The time's running, my time's running low. Let me go ahead and finish this up for you. The bond energy is going to be for iodine. This is the dissociation energy. Is going to be 151 kilojoules per mole. Okay, and the electron affinity for iodide gas is going to be minus 295 kilojoules per mole, and we're trying to find then the energy of sublimation. Okay, we're trying to find what that is. Okay, all right. So with that said, then let's quickly set this up here, and what I'll do then is I'll pick up with this problem on Tuesday, okay, because we're running low on time here. So go ahead and finish up this problem, write it down on your paper. This is the only problem that you'll be asked to submit. So make sure you write that out, submit what you have, and then write on it that we're going to finish up this problem on Tuesday. And then on Tuesday, tomorrow we'll finish up this problem, and then you can see how it's done. Okay. So please try the homework for tonight, and come on by after 3:15 today, and ask questions about what you can see tomorrow. And so what I would like to do is tomorrow we're going to start. And please go ahead and take a look at it. So this is it for ionic compounds. What we're going to do tomorrow is we're going to start the discussion on molecular compounds. We're going to talk about bond energies, and then that'll allow us to finish up chapter 8 and segue our way into chapter 9, which is going to focus entirely on molecular compounds, covalent bonds. We're going to talk about bond energies there. Okay. So good luck with this problem. Good luck with the homework. Make sure you stop on by and let me know what you have in terms of your questions. Okay. All right. I will see you folks tomorrow.